All right. So we are streaming, and it's time to get the class started. Question? We good? Okay. All right. Okay. So what we'll do today is to go over a practice exam. So 1 week from today, 184 hours, later, we're gonna have our first exam. So the first exam is gonna be 20% of your grade. Okay. For those of you who may not have remembered this from your reading the syllabus. So that's 20%, which is not a whole lot, okay? Because the second exam is another 20%. The final exam is 40% of your grade. So your homework assignment, every single lab that you do, only add up to 20% of your grade. All right? So just to keep, put things into perspective, I sent the exam to you guys, through announcement. So this is the practice exam to go over on Tuesday. And let's see, we'll open it up. So my original hope to send this ahead of time was, maybe some of you would have time to kind of read it over, first and try out those questions before coming to class. If you do not have a chance to do it, that's okay. It's not a problem. We'll basically look at those questions together, in class today. But you will miss that chance of kind of testing yourself and see if you can answer those questions without me explaining how to answer those questions. So we'll go ahead and kind of go over the read this part first, okay? Because for the most part, it is about the same for you. The time obviously is going to be different. The location is also going to be different. So the time is going to be during the lecture time next Tuesday. So it will start at 5:30. Okay. Location is going to be this room. So you basically kind of have to gauge how much room you have to bring additional material. Okay. So don't bring so much that you won't have room to spread out all your stuff. Is that okay? So the idea is every person should only use the space of one person instead of, well, I'm just going to sit where I have access to 2 empty chairs, okay? Do not make that assumption because it's not going to happen. And who's going to make sure it's not going to happen? I'm going to make sure it's not going to happen. So you only get enough space to, that is right in front of you, okay? So don't bring so much stuff that you need additional space. Okay, I'm just going to read out this part here. It's open material, which means anything that is either printed or handwritten prior to the test, you can bring with you. Okay, so what does that include? It can include all the logic sim stuff that we have done in class, okay? All the logic sim stuff that you have done, for your homework assignments. All the notes that I write, all the notes that you write, okay? If you guys want to study together, you guys can come up with the same material to bring to the test. That's not a problem. Okay? The only thing that I do not let you guys do is communication and collaboration during the exam. But collaboration for studying, hey, it's your choice. Some people like it, some people don't like it. You guys can do it however you want. Is that okay? Does that answer the question of what you can bring to the class? But no electronics, okay? You can bring a calculator with you, even a scientific graphing calculator, but no, you cannot have a cell phone in front of you during the test. Is that okay? Yep. Cannot use a laptop. So if you have material on your laptop that you think might be helpful, you have to find a way to print it out first. Okay? All right. So second part has to do with this assessment is an individual assessment. I just have to emphasize that it is an individual assessment. So that means you guys will have to work on your own test. Each person has to work on that person's own test. The answers should be independently and originally derived in the time that is allowed. So that means at the end of that one class session, I will use the entire class session, which means it starts at 5:30 and it's going to end at 6:50. But it's going to be ending at 6:50 sharp. So I don't want to see anyone, continuing to write after I say it is time, you guys have to stop writing. So even if I cannot get to all the way to the back of the classroom, everybody has to stop writing. Does that make sense? Okay, yep. That I haven't decided yet. Okay, so it depends on whether we have enough material for lab, and I think we might. Okay, so because on Thursday this week, we'll go over floating point numbers, so we may have enough material for 2 labs. So we actually may have lab after that. So do not count the lab out on next Tuesday. Okay. All right. No sharing of open material during the exam. So just because you can bring anything you want to do before the exam does not mean you guys can share material during the exam. Do you see the difference? Okay. Do not discuss the question with students who may not have taken the test after the exam. Okay, this is kind of important. Every test, someone is going to say, okay, I totally messed up this question. I just need a new sheet of paper. So bring your own additional sheets of paper. Binder paper works. I just want to make sure the edge is clear. So if you have a notebook, like those spiral notebook, that edge is kind of rugged. My scanner doesn't like that. So when you tear the page out, just kind of see if you can tear it so that it's clean. Okay. You can also just use Xerox, or copy paper and stuff like that too. If you have additional sheets of paper, make sure that your name is on each one of those, and then each paper also clearly indicates this is the answer of which question. Because otherwise, it may be difficult for me to find out whose loose paper this is and which question is it answering. So you have to make sure that I do not run into those difficulties. Yep.
Will you have a stapler?
Huh?
Will you have a stapler?
Yes, I will have a stapler. So I will have a stapler, available so that you guys can staple your stuff. Write legibly. I cannot give points to answers that I cannot decipher until that person comes back to me and say, but Tech, this really meant 1011 in base 2. That looks like squigglish to me. So, if I cannot read it, cannot interpret it, I cannot give points to it. Is that okay? All right? Make your answers as complete as possible. You want to read the questions carefully and find out what I need as a part of the answer. If you have any doubt, okay, you can leave scratch work, all the work leading to the answer on the sheet of paper. That's fine. It's not a problem. You can have additional material. I do not take points off. Okay? Because some of the questions may have partial credit, but I cannot give people partial credit if all I see is the wrong answer. If I see what leads up to the wrong answer, and some of those steps, or even the majority of those steps are actually correct, I can then have reasons to give out partial credit. Okay? Does everybody understand why your work leading to the answer is important? Okay. All the questions in that particular test in the past carry equal weights, and I intend to do the same thing this semester. The nice thing about this is you can look at every single question, and you just pick on the easy ones to start first, because they all carry the same amount of points. So if a question looks really easy, then you can start with that one. If they carry different amounts of points, then you have to factor that in. It's like, well, this is a really easy question, but it doesn't carry a lot of points. That one seems a little bit harder, but there's a lot of points over there. Which one should I start? Well, making all the questions carrying equal points makes it easy, right? You just look at all the questions. Whichever one seems easiest to you, it makes sense to start with that one. I'm assuming you guys know those tricks, about how to answer questions in an exam. If the questions cross pages, make sure you read and answer the entire question So make sure the next page doesn't have the second half of a question that you forget to answer. Once again, the first exam accounts for 20% of your final grade. So do we have any questions about this portion of the test? No questions? All right. So when you write down your name, okay, I would do this first thing, okay, not last thing, which many people do. I don't understand why. The top field is your family name. So write down your family name or last name first, and then your first name, and then your student ID. Okay? The reason why I need your last name first is because it makes it easier for me to look at the test and then enter the grade in Canvas, because Canvas only sorts by last name. Is that okay? Are we good? Oh, one more thing. When I say write legibly, that applies to your name as well. I'm hoping I can achieve 100% accuracy when I can read a name on the test and actually get the spelling of the name right the first time. My current accuracy is about 60%, because most people, instead of writing their name, they kind of sign their name instead. And go like, this is a bunch of squigglish. Let me see which student starts with a G over here. And the next letter seems to be an H. We don't have an H, maybe an N. Oh, yeah. All right, so moving on. So these are the actual questions from last semester. So question 1 of 7 is asking you, this is really cool. I give you the result of an addition, and then I ask you what x and y will give me that particular result. But it's not just the sum that I'm giving you. Okay, the sum is 1, 0, 0, 0 as a 4-bit after a 4-bit addition. That's easy, right? Because you can just say, oh, 1, 0, 0, 0 plus 0, 0, 0, 0 is going to give me 1, 0, 0, 0. That's way too easy. So I also give you the role of carry bits. So whatever you fill in x and y have to give me that all of those carry bits in addition to the sum bits. Is that okay? So that becomes a little bit more difficult. No calculator can help you with this. I know many of you have calculators that can do binary numbers, but they can only do binary addition and binary subtraction. Neither addition nor subtraction will help you with this question, because you need to know, what do you think is going to help you here? Sorry? Knowing how to count the numbers. Well, I can give you an idea of what can help you here. You can either work on the math really, really fast, because after all, x is a 4-bit number, y is only a 4-bit number. There are only 16 possible combinations for x and only 16 combinations for y. So altogether, there are only 16 times 16, which is what? 65,536 possible, answers. No, I take it back. 16 times 16 is 256. What am I talking about? Right? Yeah. So there are only 256, not even 65,000. Only 256 possible ways to fill in the zeros and ones for x and y. You just have to find out which one works. That's one way to do it. The second way to do it is to know your math. Know how the carry bits and the sum bits are calculated. So look up those equations. What is S0? How is S0 expressed? Okay, S0 is Q0 exclusive or K0. Okay? Then you have to say, well, what exclusive or with 0 will give me a 0? What do you think? Another 0, right? So that means Q0 is going to be a 0. Does that make sense? This is also going to be a 0. This is a 0 here, but we have 1 already. What exclusive OR with 1 will give you a 0? 1. Very good. So we know there's a 1 here. We know there's a 0 here, because 0 exclusive or 1 is a 1, right? That fills up the Q row. What about the X and the Y then? Kind of the same deal, okay? So let me just actually fill it in, and then we'll actually work on the math here. So I'm gonna, all right, so we have X, Y, and this is, I'm just writing it in a slightly different way here, Q, K, and then we have 1, 0, 0, 0 as our sum. So with the K is already given to you, you don't have a choice of what you can put here. So the K's or the carries are, we have an overall carry of 0, 1, 1, 0, 0. So now we have to go back in here. What exclusive OR with 1 gives me a 1? 0. What exclusive OR with 1 will give me a 0? 1. What exclusive OR 0 will give me a 0? 0. And another 0 here. So now we go back to X and Y. The nice thing about addition is it is commutative, which means it doesn't really matter which way, because it's commutative. So now I work on, now with this, you probably should work with the least significant bit first, and then work your way to the more significant bits. So in this case, I'm asking myself, I need two numbers, okay, these two, X and Y, such that X exclusive OR with Y is a 0. But in addition, I also need to make sure that X and Y is also a 0, because the carry to the next column is also a 0. So I got two restrictions. Because without those two restrictions, then I can say, oh, I can use 1, 1 or 0, 0 here. But because of the restriction of the carry bit, I eliminate one of those possibilities. 0, 0 is the only possibility here. Because if I had 1, 1, then I would have 1 instead of a 0 for the carry bit in the next column. Does that make sense? Okay. So that means I got the answer to the first column, or the least significant column, I should call that. Okay, now the next question is, I need the exclusive OR to have a 0 as an answer, but the end needs to be a 1. 1, 1. Okay, well, that seems pretty easy. 1, 1. Now I need the exclusive OR to be a 1. Oh, but what about this 1 over here? There's a carry of 1 to the next column. That is already accounted for, because this 1 plus this 1 is already contributing to this 1 here. I do not have a requirement to make sure that these two are 1, 1s as well. Because if those two were both 1, 1s, I would end up with a 0 here instead of a 1. Is that making any sense? So in this case, because it is addition, that means I can use a 0 and a 1 like this, or I can flip the order. It doesn't really matter. Because in the case of addition, well, in this case, it doesn't really matter either way. But in the subtraction, you have to be more careful, because in subtraction, it is not commutative. So we only got 1 column left. I need the exclusive OR, the result of exclusive OR to be a 0, but I also need the conjunction to be a 0. So 0, 0, yep. So we have a 0 here and a 0 here, and that's it. That's the answer to this particular question. Isn't that fun? Okay, so once we know the answer, what is the technique to answer these questions? What did I use to answer these questions?
You added some line.
I added some line. Okay, well, I did that, but that's not going to help you much in the exam. But what technique did I use? How would you prepare yourself for questions like these? What do you need to know? So we'll start with knowledge, right? Because without knowledge, it doesn't matter how smart you are, because without the knowledge, there's nothing to act on to answer the questions. So you need to have the knowledge. Where do you get the knowledge? The notes, studying, the modules, the labs are kind of in designed to help you with that as well, okay? But most of all, is the notes and also the lectures. Okay, you may not want to rewatch every single minute of every single lecture. Okay, that's not doable. But if you say, okay, there are only key elements that I need to review, okay, like how the Q terms are defined, how the sum terms are defined, which one is the sum, which one is the Q again, you can look up the videos and kind of rewatch that explanation. Is that okay? Does everybody know how to use YouTube? Other than entertainment purposes. Because most of you know how to apply YouTube in an entertainment situation. It's like, oh yeah, we know how to skip over certain things, but you just have to reapply those skills for recording of this class. Okay, so that's the first one, knowledge. What is the second ingredient that you need? Because someone who just have the knowledge is going to say, I know how Q is defined, I know how K is defined, but I don't know how to solve this problem given those knowledge. So what do you need to solve the problems? Truth table. Truth table is useful because you need to know what is exclusive OR, the truth table of exclusive OR, and in this particular case, the truth table of conjunction is helpful as well. Now, conjunction is not too big of a deal because most of you already know what it is, okay? What else? So all of those are raw ingredients that you need to throw into the box. So once you have all of these ingredients in the box, how do you say, I need to work out this bit here. What is that going to be? You know the result of the exclusive OR is a 0. You know in the expression, one of the value is a 0. You look up the exclusive OR truth table, and you ask, okay, what can the other number possibly be? And the truth table will say, it can only be a 0. Okay, so that's how you apply those techniques. That will get you these 4 digits really quickly. The trickier ones would be the x and the y, because you got 2 constraints. So this is a particular way of solving problems. It's constraint-based reasoning. You're looking at all the rules, and you say, there are rules that can be applicable here. I can only have certain things that can happen. So when you try to work out these 2 digits, then you ask yourself 2 questions. The first question is the same thing that you already asked yourself many times already, is I know the answer of the exclusive OR is a 0. What 2 numbers can give me a result of 0? Then the answer to that question is 0, 0, which can give you a result of 0. 1, 1 can also give you a result of 0. Then you have to think and go like, well, can I use both? Or is one of those not applicable in this case? So in that case, you have to look up these 2 and go like, well, if both of these are 1s, then I would have a carry of 1 over here. That conflicts with what is given in the question. So you have to rule that out. That constraint is basically saying that only 0, 0 applies here. 1, 1 does not apply. Is that okay? So I'm trying to explain my thought process of answering this question so that you can not so much to exactly copy that technique, but a technique is to look at all the constraints. But it starts off with the definition of the terms. It started with the definition of the operators, the truth tables. So all of those. Question? No, no. If you guys have a question, I can answer that question. Okay. Is okay? All right. So are we okay with question number 1 of 7? Yep.
Can I have another example?
Oh, wait. He raised his hand first, so I'm gonna
Yeah, how do you find Q again?
find Q.
Yeah, the thickness.
You mean the entire row of Q?
Just Q. Yeah.
By its definition? All right, so what is Q? Where do I find Q in my notes? In the binary addition notes. Very good. Okay, so for those people who squinted and go like, I have no recollection of any discussion of the Q terms, it is time to study. You got 1 week, you got a little less than 1 week to do it, okay? Because without the knowledge, there's no way you can answer the questions. For those of you who say, I know where to find it, okay? Then you go to the notes, when you look it up, you will find that Q is defined to be, okay, so Q of I is defined to be the result of adding x of I to y of I. There's one section that uses the R term, and then there's another section that talks about, oh, by the way, if these digits are binary, then R is exclusive OR. But exclusive OR is sometimes not available as a logical operator, and then I translated that into x not y or not xy. Okay? But it is exclusive OR. So that's how the row Q is answered. So you have to find out exactly what that means. You have to come up with a truth table of exclusive OR to answer that question.
That's my question. I know how to solve the addition, binary addition, but my question was, how do you going from the left side to the right side, filling out those gaps on the queue very fast?
The queues, it doesn't matter whether you go from left to right or right to left. The reason why it doesn't matter is because to get to this row, you only rely on these 2 digits to determine this digit. These 2 determines this, these 2 determines this, these 2 determines this. So that's why it doesn't matter which way, because there's no carry involved. But when you talk about x and y, then there's the carry involved. Adding these 2 digits can contribute to this carry. Adding these 2 digits can contribute to this carry, and so on. So x and y is a little bit more difficult because there are 2 rules that apply to those digits instead of just 1 rule. Is that okay? Are we good? All right. So if you guys want to help each other to practice, you can just come up with some random number in addition, and then just erase 1 or 2 rows, okay? And then have the other person to say, okay, fill in these blanks. Okay? And working on subtraction would help too. Question 2 of 7. Convert the following number into base 10 step by step. What that means is the steps in carry points. That's basically what it means. So where do we start with this one? Okay? First of all, what is the base of the given number? Base 4. How do we know it's base 4? Because of the subscript. Okay, so the subscript 4 indicates this number is a base 4 number. It is representing a value, and I need you to convert that value to base 10. But I want you to do it step by step, which means you have to show me that you understand how a value is represented as a number. So what is that? How are we going to do that? So the first thing we'll do is we look at 131.3. Okay, I'm not going to call this 131 because it really is not. Okay, it is 131.4.3 as a base 4 number. So I'm going to write it out as it's 100 in base 4 plus 30 in base 4 plus 1 in base 4 plus 0.3 in base 4. Okay? Do you think this separation of digits will work regardless of the base? Yeah. If I give you like base 7, it's going to be the same process. Okay? Because all I'm doing is to disassemble the number to basically say, how many 100s do we have? We got 1 of those. How many 10s do we have? We got 3 of those. How many units do we have? We got 1 of those. And how many 0.3s do we have? Or 0.1s do we have? We got 3 of those. So the next row is going to look like this. So we have 1 times 100 in base 4 plus 3 times 10 in base 4 plus 1 times 1 in base 4 plus 3 times 0.1 in base 4. Do you think that from the first row to the second row, it depends on the base that we're dealing with? Not at all. Okay? Because all I want to do is to say, hey, look at this. It's 3, 0. Let's rewrite it as 3 of 1 zeros. It works across any base. But this is already the beginning of base conversion, because you can notice how this 1 does not have a 4 in parentheses, because that's already in base 10. This 3 is in base 10. This 1, this 3, those are already in base 10. So now, the next row is going to basically finish the entire conversion. This is 1 times 4 to the power of 2 plus 3 times 4 to the power of 1 plus 1 times 1 to the power of 0 plus 3 times 1 to the, excuse me, I take it back, okay, my fault. 3 times 4 to the power of negative 1. Yep.
If we jump straight to that step, would that be okay?
You can jump straight to that step. So if you start from here and you jump to this step, I will still count it as correct. But for explanation, I want to do it really step by step. Okay, so do we have any questions about the second row to the third row of this derivation? Yep.
For our answer on the test, do you want a written explanation too?
I want it to look like this, so it can all be numbers without words to explain.
Okay.
Yep. So technically speaking, this is already done with a base conversion. I do not have a base 4 number anymore. You don't see anything in parentheses 4, which means I'm dealing with all base 10 numbers. So the next step is really just to carry out all of these multiplications and powers and stuff like that. So we got 16. This is going to be 12. This is going to be 1. And what is that going to be? 3/4 or 0.75. All right. So we just add up these numbers. This is pretty much the only time a calculator can come in handy. If anyone can give me up to this step and then just kind of mess up, with the calculations, that person is going to get most of the points. I mean, seriously. I mean, I'm not really testing whether you guys can carry out arithmetic operations. I'm testing whether you understand the concepts. So in this case, it's going to be 28, 29, so 29.75, I think. Yep. All right. Yep.
Can we use the equation and plug in instead?
The equation. That one is not going to help with this question, because that one converts to whatever base I want you to convert into. This one figures out the value of a number in a particular base. So if you want to plug in, this is actually the sigma. The sigma, V equals to sigma di times b to the power of I. That is the equation that you're going to be plugging in, which is basically the same thing that expands out here. So that's why if you jump all the way to the third row, that's the application of that sigma notation. So are we good so far with question number 2? Okay, very good. And then we move on to question number 3. I don't have to scroll the PDF. I just have to kind of move on here. So question number 3 is asking the opposite. I give you a value in base 10. You'll see how this number does not have a subscript or parentheses. So that means it is already expressed in base 10. So we are, in fact, talking about 32.84 in this case. And the question is asking you to convert into base 5. And once again, it needs to be done step by step. So how would you do that? So this is where the digit thing can come in handy, but you don't have to do it that way. Okay? So I can do it this way without using the equation that is actually mentioned in my notes. If you apply that, that's good too, okay? So in this case, I'm basically asking, I have gotten, some, okay, so give me the largest power of 5 in 32.84. 25, okay, very good. So I can say this is a 25. So with 25 taken care of, I have 7.84. Okay, so if I want to really do it in step by step, then I focus now on 7.84 and I ask, what is the largest power of 5 or largest multiple power of 5 in 7.84? 1 of 5, okay? So I have 2.84 left. So now the question is, what is the largest multiple of 5 to the power of 0 do I have in 2.84? I have 2 of 1, okay? So I'm just going to make it a very important point here to say I have 2 of 1s. In other words, I'm asking, well, the other ones are kind of 1 of 25, except the 1 of is kind of implicit. But I want to figure out how many of each power of 5 do I have. So you kind of have to be careful about that question and go like, if this is like 52.84 to begin with, then you will have 2 of 25. Okay? So, but I cannot stop yet because I'm not quite done. So now I'm on to 0.84, okay, which is a base 10 number. And I ask, what is the largest multiple of a power of 5 do I have in 0.84? So now the question is, well, we are done with all the non-fractional part because we took care of the 1 here already. So what is the next power of 5 that we are dealing with? Negative 1. 5 to the power of negative 1 is 1/5, which is also known as 0.2. Okay? So now my real question is asking, how many 0.2s do we have? 4 of those. Very good. So we have 4 times 0.2, okay? However you want to write it, plus the remaining portion, which is 0.04. But we don't end here because 0.04 seems like it is already done as a base 4 number. You still have to kind of go through that process once, okay? Because it is not what it seems. Because you guys may remember, okay, I made that mistake of using a digit that should not exist in a particular base, right? And you can say, oh, 0.04 seems like it's a base 5 number already, because in base 5 we cannot have 5, but we can certainly have 4. And this is taking care of to the power of negative 1. That seems okay already. We are not done yet, okay? Because we just took care of 5 to the power of negative 1. Now it's time to take care of 5 to the power of negative 2. What is 5 to the power of negative 2? It's 1 divided by 25, which is also known as 0.04. And we got how many of those? 1 of those. So that is why the last digit in this particular question is a little bit tricky, because you have to say that we have 1 of 0.04. So now we have quantities of each power of 5. 5 to the power of 2, 5 to the power of 1, 5 to the power of 0, 5 to the power of negative 1, 5 to the power of negative 2. We have nothing remaining, so we are done with the first part of the conversion process. Are we good so far? Okay. So now I need to rewrite this. Now 25 is 5 to the power of 2. This is 5 to the power of 1. This is 2 times 5 to the power of 0. And then the rest, you probably know what we are going to say here. 5 to the power of negative 1 plus 1 times 5 to the power of negative 2. And this may be a good place where the 1 times becomes significant. So we got 1, 0, 0 in base 5 plus 1, 0. Whoops, in base 5 plus 2 in base 5 plus 0.4 in base 5 plus 0.01 in base 5. Do we have any questions here? Because if you ask me what is the line, the one line that does the base conversion, this is it. But does it make sense to you? Because this boils down to number representation. What does 100 in base 5 mean? It means we have no 1, we have no 5, but we have 125. That is what it means when we have 100 in base 5. Is that okay? Are we good so far? Okay. So the next step is just really put everything together. So now we have 112.41 in base 5, and that's our final answer. And once again, if you can get to the second last step, but somehow did not copy the digits correctly to the last row, you will get some deduction, but it's not going to be major. You'll get most of the points. Yep. The second last step, you mean this one?
Yeah, skip that one.
So go from here to here? Yeah, you can do that. Yep, because it still expresses that you know that we are dealing with how many the quantity of each power of 5. That's the important part. So yes, you can skip the second to the last step, and I will still give full credit. Yep. Do we have any questions, particularly conceptual questions, regarding how a value is represented by numbers in different bases? No particular questions? Okay. Since I have used the base 4 and base 5 here, maybe look into base 3 and base 7 for practice. So are we good so far? Yes? Okay. Number 4. So question number 4 is this is a strictly conceptual question. So let me show you what the question looks like. All right, so here's the question. We are considering a carry look ahead adder. So the first thing is, do you know what is carry look ahead? What does it mean? So if you know what is a carry look ahead, then you also have to know what is not a carry look ahead. What is the other type of adder? Okay, so make sure that in your mind it is clear that we have carry ripple adder and then carry look ahead adder. Okay, those two are mechanically very different. If the final OR gate to compute K10 requires 11 input ports, how many input ports do we need to compute K20? So please write your answer, your number of ports, as well as the reasoning of your answer. So you have to give me a number, like this many ports, but then you also have to answer the question of why you think that is the case. All right, so how would you approach this question? Starting with knowledge. Where is the knowledge that you need to answer these questions? In other words, what are the indicators, what are the indicator words in the question itself that will help you identify what knowledge is needed to answer this question? Carry look ahead, very good. So the first thing is to understand what is carry look ahead, which is section 6 of the binary addition module. Okay, so that entire section 6, talks about carry look ahead, the mechanism of carry look ahead. And then, it just out of nowhere, it mentions something about an OR gate. So then what is the next thing you're going to look up? You can look up the examples of K1, K2, K3. Those were worked out already for you, right? Okay? But the question doesn't say anything about K1, K2, or K3. It skips all the way to K10. So what are you going to do? look up that expression. Okay? So let me show you the expression here. Okay, so and by the way, for every single module that I write, there's one version in PDF and one version in HTML. So when you click on the note here, you can see there's a PDF and there's also HTML. Depending on which one you prefer, you can print the PDF version or the HTML version. The HTML version kind of depends on the browser, how well it renders. The PDF usually should not have any problem rendering on the printer. So, that part is up to you. The HTML version does have the option of, you can change the font size, I think, on most browsers. So we are looking at section 6. Okay, so we go to section 6. But wait, there's more, blah, 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 blah. Okay, so we look up K1. So how many input ports do you think the OR gate has in K1? We got 2, because, wait, but there's no OR, there's just a plus here. Because plus means OR in a Boolean expression, okay? If you got to understand the shorthand that I have been using for the past 4 weeks, okay? So it has got 2, okay? So K1 needs 2 input ports for the OR gate. There are 2 things to OR. K2, we only got 2 things to OR. Am I looking at the right row? Look at the last one, right? We got 3 things to OR together. Okay? Look at K3. How many things do we have to OR together? 1, 2, 3, 4. So, well, it seems to make sense. That is not a good answer. Okay? If you answer, I think it needs this many because it seems to make sense, that is not a good answer. So how do you answer the question? This thing here. Whoa, how do we look at this thing? Well, this is a big OR, right? So if I ask, what was the question? K20, right? Okay. So if I want n plus 1 to be 20, what is n? 19. Very good. So how many items are we ORing here? From 0 to 19, how many iterations do we have to go through that loop? 20 iterations. Okay? But there's one additional OR here. There's one loose term that has to be ORed separate out from the big OR. So we got 21 terms altogether. That is how you answer the question. Okay? So you have to find out where the knowledge is in the notes and know how to apply the knowledge to answer those questions. Are we good so far? Yes?
What was the other type of adder called? What was the other type of adder called?
The other type is called a carry ripple adder, because it ripples the carry along. Or for the purpose of this class, you can just say it is a non-carry look ahead. Yes?
So putting this down would be a sufficient answer? Would you require further explanation?
I would, answer the question by saying, since we are trying to figure out K20, n is 19, and this term going from 0 to 19 will give me, 20 terms to OR, plus this extra term, now we have 21 terms. So I would explain, that. Is that okay? Because I'm looking into your reasoning. The points are related to your reasoning. So that's why you have to kind of explain your reasoning behind it. Is that okay? So I think we got only one question left in the practice test. All right, so question number 5 of 7 is the last one, even though there are 2 additional questions, but because they ask about something that we have not talked about, so those are out of the scope as far as you are concerned, okay? So question number 5 out of 7, it asks, step by step, derive the signed value represented by the following 6-bit binary number. Okay, so where is the knowledge? Signed versus unsigned values, okay? Signed value representation, okay. So in that note, okay, where does it explain how to derive? Well, there are actually 2 places, by the way. The comparison thing also has it. And in your test, comparison is in the test. It is within the scope because we talked about comparison in this class. So I changed the ordering of the questions, changed the ordering of the material a little bit. So that's why last year comparison, it was not on the test. But for you guys, comparison and subtraction will definitely be on the test. So I can give you some additional questions to chew on, maybe just a little bit, but we'll work on this one first. So how do we find out the signed value represented by this particular 6-bit number? So you have to find the knowledge first. The knowledge is in, okay, so let me find the module first. So the knowledge is contained partially in binary number comparison, and partially it is in signed value representation. Okay, it's just a little bit different, but it's actually in both. So I think the best one is actually in binary number comparison. So let's click on it and find it. So you look it up, and we'll look down. There's one big sigma thingy that we have to deal with. Signed interpretation. This is it. V of x equals to blah, 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 blah. But you don't have to remember the derivation. Look at the last one. That's your answer. So what you have is I'm giving you the 6 bits. I'm giving you x0 to x5. And your job is to plug in x0 to x5 in the sigma and the extra term that we have here. Is that okay so far? Okay. What is your m, by the way? So I'm giving you a 6-bit number. So what is m? M is?
The 64, the width of the machine width.
But what is going to be your m when you try to answer the question that I was presenting earlier? You have a 6-bit number, right?
Oh, 6.
Yes, m is 6. Very good. Okay, good job. So m is 6 because here it says given m bits and you're given 6 bits. So the m that you have to deal with is 6. So now you have to go, and use a loop. I goes from 0 to 6 minus 2, which is 4, right? So you basically have to multiply the digits x subscript 0 to 2 to the power of 0, x subscript 1 to 2 to the power of 1, blah, 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 blah. So there'll be 5 terms here, minus x5 times 2 to the power of 5. Whatever that sum turns out to be, that's your answer. So this one does not even need a whole lot of problem solving. Once you find the sigma notation, it's like, apply that. Do we have any questions about this one?
Can we solve it?
Yeah, we can do it. So I first have to copy the question. Let's see. And then we go back to the definition. So I can show you the equation. And then we go to, where's my mouse pad? Oh, there we go. There we go. Okay, so we'll figure it out, right? So we have 0 times 2 to the power of 0 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 2 plus 1 times 2 to the power 3 times 0 times 2 to the power 4 minus 1 times 2 to the power of 5. Is that okay? Where do I get all those zeros and ones? This 0 comes from here, this 0 comes from here, this 1 comes from here, and so on. Are we good so far? Yep.
Couldn't you use two's complement?
You can also use two's complement, but if you use two's complement, then you, okay, can you explain a little bit more when you said, can't we use two's complement?
You invert the value, whatever the sixth bit value, and you add 1.
But why do you apply two's complement? You have to explain to me why you are applying two's complement. So can you tell me why you're applying two's complement? No, you already know the answer. Just because you said that can we apply two's complement means that in your mind you knew why you want to apply two's complement. You just have to verbalize that reason. Okay, what is two's complement equivalent to as an operator? The negation of, arithmetic negation. But why did you think of arithmetic negation?
The number wheel?
Because what?
The number wheel.
The number wheel. What about the number wheel? The number wheel has many things, but what is the reason of you mentioning the number wheel? It's got to be this one here. Because the sign bit is a 1, so that means the value it is representing is negative. But you want to know how negative it is, so by taking two's complement, you're basically taking the absolute value of the signed number, so you know how negative it is. So let me finish this first, and then I'll explain the other way to answer this question. So this one is 4, this one is 8, this one is 0, minus 32. So when you do the calculations, it's 12 minus 32, which is negative 20, I think. Is that about right? I don't like arithmetic stuff, so. Is that right? Okay. All right. So now we use the other method. Okay. So we can say the negation of 101100 in base 2 should be the same thing as what it was originally. Does that make sense? Is that okay? Does anyone want to refute and say double negation doesn't get us back what we started off with? Is that okay? All right. So let's go. So I will keep one arithmetic negation, but I'll change the other one to a C2, two's complement. Would that be okay? All I did is to say, of the two arithmetic negations, I keep one as it is, but I changed the other one to two's complement, which I claim to do exactly the same thing as arithmetic negation when you have fixed width calculation in base 2. Is that okay? Right? Okay. So what is that going to give me? So now we have to look at what is two's complement. Two's complement, by definition, is 1's complement, 1, 0, 1, 1, 0, 0 in base 2, plus 1. Okay? And that's going to give us what? 0, 1, 0, 0, 1, 1 in base 2 plus 1, which then gives me 0, 1, 1, 0, 1, 0, 1, 0, 0 in base 2, right? Now you have to do a base 2 to base 10 conversion. So in this case, we have 1, 4 plus no 8, 116. And we get negative 20. So we get exactly the same result back. So if you apply 2's complement, then you have to use this line of reasoning. Because I have to know why you choose to apply 2's complement. If I give you a number where the most significant bit is not a 1, you would not apply 2's complement. It doesn't make sense. So the fact that you are using 2's complement, you have to explain the rationale behind that. Does that make sense? Or is that okay? Okay. All right. Yep.
We basically have to understand the summation notation and just represent, just insert it in the line.
Yep. Summation. So the previous one, this one uses the summation definition. This one uses the 2's complement method to find the same value. So they're both valid. They're both as correct as each other. You can use either one. It's just that if you use one, either one you have to explain, and derive it. Yep. I have not decided yet. Oh yeah, it's definitely more than 5. So I can guarantee it's more than 5, but I don't know how many more than 5. Okay. So what about comparison? Don't you guys want to work on some comparison stuff? Okay. All right. So just out of nowhere, okay, I'm just giving you a question right here, okay? Give me an example where after a subtraction in binary, the overall borrow is 0, but the sign, but the L bit is 1. Okay. And I'll give you a fixed number too, so so we'll just deal with 3-bit here. Okay. So this is your question. First of all, okay, what kind of knowledge are we talking about here? And given the knowledge that we already know, how do we apply this? How do we apply the knowledge to solve this problem? I'm pretty sure it's still recording. Let me just double check. Yep, still recording. And the cricket is getting recorded too. All right. So how do you solve this problem? What kind of knowledge are we talking about? Just from the question itself. So binary subtraction. So the first keyword, binary subtraction, is a 3-bit operation, which means the difference should only have 3 bits with 4 borrow bits, right? You also need to know how the borrow bit is computed, and you also know what the L bit is. What is the L bit? Do you guys remember the sign bit is not totally reliable, right? So how do we fix that problem that the L sign bit itself is not always reliable? Which bit did we come up with and say that, well, sometimes that sign bit is not reliable, and I will tell you when that thing is not reliable. How do we call that bit? Overflow. Very good. So now we have the sign bit, we have the overflow bit. How does the L bit relate to the sign and the overflow bit? Yes. So the sign bit refers to the most significant bit of the difference after a subtraction. The overflow bit, in your lab that was due earlier today, you got, you worked on that already. So what is the L bit? How do we combine the sign bit and the overflow bit to become the L bit? Yep.
If the overflow is 0, then the L bit, or the carry bit is also 0. Basically, the overflow
Okay, so let's look at the truth table. We got the sign, we got the overflow, okay? The overflow is basically saying, is the sign bit lying? Okay, that's what it's asking. What do you think the L bit is saying? Under which module are these concepts discussed? Binary number comparison, right? And which one comparison operator do we care about? Exclusive or, very good. So you raise your hand.
I was just gonna say that it means that the minuend is less than the subtrahend.
Exactly. So the L bit is a 1 if and only if the minuend is less than the subtrahend. That's what the L bit is indicating. Okay? Is the minuend less than the subtrahend? Okay? All right. So if the sign bit is a 1, overflow bit is a 0, is the minuend less than the subtrahend? The sign bit is not lying. The sign bit of the difference is the way it's supposed to be. So is the minuend less than the subtrahend? Yes. Okay. Okay, so you guys kind of have to remember how this stuff is derived. Okay? We are trying to figure out whether x is less than y. That's what we're trying to figure out. But we can also do some little algebra thing, and this is how we derived it. Do you remember this part? So we can theoretically look at the difference between the two numbers. If the difference is less than 0, then the minuend x is less than the subtrahend y. And that's why we started off with the saying, oh, that's great, because now the sign bit can tell us about the result of a comparison, is x less than y. But we found problems with that approach, because sometimes you end up with an overflow, then the sign bit cannot be trusted, because the result of after subtraction is a value that cannot be represented given the number of bits that you have. That's what the overflow bit is trying to say is, oh, we ran out of bits to represent the result after a subtraction, so the sign bit is wrong. Okay? So getting back to the truth table, what about this? What if the sign bit says, yes, x is less than y, and then the overflow bit says, no, he's lying? Then is the minuend actually less than the subtrahend? No. Okay, very good. Sign bit is a 0, and the overflow bit is also a 0, basically saying, yep, you can trust the sign bit on this one. What do you think? Is the minuend less than the subtrahend? Nope. Very good. And the last one is this. What do you think? Yes. So when you look at the L flag, how does it relate to the sign and the overflow flag? It is exclusive OR. Very good. So the L flag is the exclusive OR between the sign and the overflow flag. Is that okay? Pretty sure we talked about this. And it's also in the module. That's the best part of recording my lectures, because I can now say that. And then the next class, I can say that I said that in the previous class. I can do it recursively now. Today is the base case. Okay, so given this, can we now answer this question? Let me give you a better way to represent this. Okay, I'm trying to figure out this: x2, x1, x0. So those are the digits of x, minus the digits of y: y2, y1, y0. These are the digits of y. And just like usual, we have the q row. Okay. And because this is a subtraction, we have the t bits. Okay. So we have t3, t2, T1, and T0. These are my T bits. And then we have the difference, which is the actual result after the subtraction. We got D2, D1, and then D0. So what I want you to tell me is, give me an example of X and Y. Both are 3-bit numbers, so that the sign bit, so that the borrow bit T3 is a 0. I want the result to be that. And I also want the L bit to be a 1. Okay? And in a question like this, very typical of me, it will say, if you think it is not possible, explain why it is not possible. Okay, first of all, is it possible? It is possible. Okay. So if it is possible, how do you get it to work? Okay. So once again, it is a question of knowledge first. Then you apply reasoning on top of knowledge, right? Just looking at T3 and L is not going to help you. So you have to understand what they are representing. We start with L. So in this case, how do you represent the sign bit, or T3? D2, sorry. We'll start with D2 first. So how do you express, well, okay, I take it back, excuse me. I keep flip-flopping, but I'm taking it back here. So we'll start with the overflow flag. How do we define the overflow flag? This is from the lab from last week. Okay. So not x2 in this case, because we have these symbols here, y2 d2, or x2 not y2 not d2. Okay. And then here's the question. Tech, do you really expect me to remember the overflow bit definition? No. I expect you to bring your notes and know where to find in the notes. Okay. So we know overflow is like this. But we know the L flag is the exclusive OR between the overflow and the sign flag, right? So now we ask the question, what do you think D2 needs to be in this case? Oh, this is too much. So you have to basically say, if D2 is a 1, then this expression becomes important. If D2 is a 0, then this expression becomes important. Okay? So we have all of these pieces here. Okay? These are all basically just based on definitions. What do you think? How would you solve this problem? I think it's easier with the truth table. You can use a truth table. You can see that the overflow has to be 1. The overflow has to be 1. D2 has to be a 1. Why do you think D2 has to be 1?
Because the sign and the overflow are exclusive OR, which means that the L is a 1. The less than is a 1, so I guess if you do it. So I like where you're starting, because you're applying the truth table here. We know that the L flag is a 1. That's what we want to achieve. So we can either have we can either have D2 being a 1 and with no overflow, or we can have this scenario happening here. So both will satisfy the requirement of L being a 1. Yes?
But in a problem, it says overflow bar is 0, right?
It says overflow, it says borrow has to be a 0. So we know there's a 0 here. Okay? Is that going to help me? Quite a bit, actually. Okay, so let me go back and change here. Based on the question, we have this constraint already. How is that constraint going to help me? It doesn't seem to make sense. Well, it tells me that x2, y, I cannot have 0 and 1 here. Right? Because that will give me a borrow right the way being a 1. Okay. So now so once again, it's constraint-based reasoning. These two can be the same, or we can have a 1 and a 0 here. It's one or the other. Is that okay? So let's say that we forget all of the other bits because they're really not needed to come up with an example. So we'll work with 0, 0 here. If they're both zeros, what will happen? 0 minus 0 is a 0 with no borrow. And then 0 minus, it depends on whether this is a 1 or not. But if this is a 1, we end up with a borrow here. So the fact that this is a borrow means it's 0 minus 0, which is also going to be a 0 here, which means the sign flag is going to be a 0, but it's also not overflowing. So it doesn't satisfy the requirement of L has to be 1. Okay, so that doesn't work. What if these two are 1, 1? Well, let's see what happens. 1 minus 1 is a 0 with no borrow. So far, so good. 0 minus something cannot give me a borrow, and yet it has to give me a sign of 1. That's not going to happen. We only got one choice left, right? Which is x2 being a 1, y2 being a 0. What is that going to give me? 1 minus 0 is a 1 without a borrow. 1 minus whatever t2 is going to give me d2. So we can assume all of these are zeros. So we can assume t2 is also a 0. So 1 minus 0 will give me a 0. Will that give me what I want? So it will give me x2 being 1, y2 being 0, d2 being 1. Right? But is that satisfying the requirement that I need? Yep, it does. Because overflow is going to be 0. We do not have an overflow situation, but the L flag is going to be a 1 because L is the exclusive OR between D2 and overflow. So that is one way to solve the problem. There's another way to solve the problem. Okay? If you do not like bitwise operations, if this kind of stuff gives you headache, then you have an alternative. The alternative is to look at the meaning of the borrow flag versus the L flag. The L flag says, in signed interpretation, x is less than y. The borrow flag says, in unsigned interpretation, x is less than y. So the question is really asking you, for the same 2-bit patterns, do we have a case where if interpreted signed, x is in fact less than y, but if interpreted unsigned, x is not less than y? Is that helping? Okay. So we'll take a look at here. Okay. So I'm saying x is 1, 0, 0 in base 2, and y is 0, 0, 0, 0, 0 in base 2. What is the value of x when it is uninterpreted unsigned? What is that? You can look up the number wheel. It's 4. Okay, very good. What about the signed interpretation of x? You can look up the number wheel. 4 is kind of like a tricky one because that's where things go kind of like really awkward. Negative 4. Okay. What about unsigned 0? Unsigned 0, 0, 0 is 0. Signed 0, 0, 0 is also 0. Oh, we got our case, right? 4 is not less than 0. Therefore, the borrow flag is a 0 because the borrow flag indicates less than in an unsigned comparison. But we also have negative 4 being less than 0 in signed interpretation. That's what the L flag is for. The L flag is an indicator of less than, but only in signed interpretation. So yeah. Oh, okay. It is. No, this is right.
Oh, okay, I see. So we got, oh, okay, I see. So this is Y. No, this is right. Oh, never mind, never mind. Alrighty. These are two are both Y's. Okay, I flipped the X and the Y. There we go. Now it's correct. So once again, but stepping up, from the perspective, you got two ways to solve the problem. You can look at the bitwise operations and do constraint-based, reasoning, and try to find out, okay, how do I make this, how do I meet all of these constraints? But you have to look up the definitions. You have to be good at your bitwise operations, truth tables, and stuff like that. And you have to be willing to try out several combinations and see which one works. You can also look at this from the perspective of the meaning of the flags. What is the B flag? Okay, it's the borrow flag. But what does it mean when it's a 1 after a subtraction? It means the minuend is less than the subtrahend when interpreted unsigned. Okay, that's basically what it means. What about the L flag? Well, the L flag is the exclusive OR between the sign and the overflow flag. Yes, mechanically that is how it is computed. But what is the meaning of the L flag? It means the minuend is less than the subtrahend interpreted signed. So those are the alternatives. You can look at it from the perspective of semantics. You can also look at it from the perspective of bitwise operations. Okay? I don't really have a new lab for you guys because we didn't go over floating point numbers. So, we can still go to the lab. You guys can still ask me questions, but there's no structured lab activity for today. I would use this opportunity to ask me questions. Yep, go ahead.